Hey guys, this is section 2.1, derivatives and rates of change. Um, Here's your FLT. Go ahead and pause and play whenever you're ready. So you're going to be given a scenario. Most often cases, you're going to be given an equation where you have to find the derivative at a particular moment. So that's the procedural stuff. But make sure that when you guys are learning all of these techniques, you don't lose the meaning behind what a derivative is, okay? So So remember our exploration, okay? In that last lesson, right? We were able to derive this definition right here. Now, go ahead and write it down and then play when you're ready. But let me break this down for you guys. Everything in purple here, look back in your notes, but think about where we got that from. What does this purple represent? Just that purple piece, okay? So if you remember when we had a random function and we picked two random points, we were able to find the slope of a secant line. This right here in purple is the slope of a secant line. Give me some synonyms, right? What's another synonym for slope of a secant line? Average rate of change, AROC. Okay, that's your toll booth scenario where that guy had to pick up two different receipts to find out that you were speeding, right? So here you had two data points. Okay, now my second question to you is this in green, what does that do to your picture? Remember, what does it mean when h goes to 0? Okay, pause and play when you're ready. When h goes to 0, h represents the horizontal distance from the 2 points. So if h is going to 0, that means that the distance between these 2 points are going to 0, meaning that these 2 points are getting closer and closer and closer and closer to each other to the point where they overlap. Okay? Now think about what it means when these 2 points overlap. Okay? It creates a line that intersects the curve once. We call that slope of a tangent line. Okay, also known as the instantaneous rate of change. So this right here, this limit part is what makes it instantaneous. If we neglected that limit part, it just makes it an average rate of change. So that limit is what makes it instantaneous. So this concept is so important that they gave it a notation here. So right over here, the way you would read that is f prime of x. Okay, that notation right there is prime. If you've taken physics, you've seen that before. F prime of x. Now, some notations to get out of the way. Let me make some space for you guys. Okay, so this is the way to write a derivative. A derivative is the instantaneous rate of change. The derivative is the slope of a tangent line, okay? So you can see derivatives in many different ways, okay? So f prime of x or g prime of x or h prime of x, whatever prime of x is derivative, okay? Sometimes they'll even just say y prime, all right? Sometimes they'll use this as well, dy over dx. Okay, it's just different notations. Some of them are more advantageous than the other depending on the context of the problem. But all of these three notations right here is what you'll normally see representing the derivative. So don't forget, derivative means you're finding the slope of the tangent line, okay, or the instantaneous rate of change. You'll hear me repeat that a lot, all right? So that's the context behind it. We're trying to find out how fast something is changing or the rate of it at one particular moment. So we have this figurative radar gun that we're now allowed to use. We can find out how fast anything is changing at one particular moment. Okay? So the next part here is, well, how do we actually use this? How do we put this into action? Okay? So here's example 1. Pause and play when you're ready, but write down this problem. So example 1 here, we are asked to find an equation of a tangent line to the parabola y equals x squared at the point 1, 1. Okay, so before we get into the procedural stuff is easy, okay? I want to make sure that you guys understand the concept of this, okay? We have this parabola, and you don't have to draw it out. I'm giving you guys a visual here. We have this parabola, and specifically at 1, 1, they want us to come up with the equation of that tangent line. So if I were to draw a tangent line here, we're pretty much coming up with, well, what's the equation of that tangent line? Okay? You guys will see this phrase a lot, equation of a tangent line. Anytime you guys see that, and I'll remind you through every example, anytime you need an equation of a tangent line, you need 2 things. You need the slope, and you need a point. Always, always. Okay? If you take a look at this problem, they already give us a point. It's 1, 1. So we know where we want this tangent line to be. We want it at 1, 1. So all we're missing here is our slope. Now, how do you find the slope of a tangent line, right? The slope of a tangent line is really the derivative, or the instantaneous rate of change. So here's what we do. I'm going to write it out as often as we need to remember it, okay? So remember, the derivative, f prime of x, is equal to the limit of f of x plus h minus f of x all over h as h approaches 0. Make sure you guys pay attention to how you're saying it and how you're writing it, okay? So how do we figure out what's what, right? So they give you a function, y equals x squared, but if it makes it easier, call that f of x equals x squared. Because remember back in Algebra 2 or IM 2 or 3, y is the same thing as f of x. It's just a different label, okay? So if you take a look at this here, here we have the limit as h approaches 0. I have a h down below. And right here, I have an f of x. Do I know what f of x is? I do, it's right here. F of x is x squared, right? So I'm going to plug f of x in there. F of x is x squared. That's the easy part. Now this part here is where some people tend to get confused. But we need to figure out what f of x plus h is. So kind of like the exploration that we did. If you guys know f of x is x squared, what's f of x plus h, right? So pretty much what you do here is you substitute the x for an x plus h. So f of x plus h is equivalent or equal to the quantity x plus h squared. The square goes on the outside of that quantity there, okay? That is probably the toughest step. Okay, now if that was easy to you, the whole thing is going to be easy here, okay? It takes some getting used to because we're not familiar with this type of language, but with practice, you guys will get there, okay? Now the rest here is the same thing as the exploration. We're going to clean this up a little bit. Now, I am not taking the limit yet. I'm just going to clean up what I have. So down below, I have an h. Up top here, in this quantity, I'm going to go ahead and expand that. Okay, so if you remember, the shortcut to expanding a perfect square is you square the first term, so that's x squared. You square the last term, so that's h squared. and then you multiply the two terms together, and then you double it. So x times h is xh, and if you double it, it's times 2. So in the middle is going to be 2xh. All right? Everything else I'm just going to bring down. Minus x squared all over h. All right? Let's keep going. So I noticed that x squared minus x squared will go away. And I notice here I have 2xh plus h squared all over h as h goes to 0. So I noticed that if I try to plug in 0, I'm not going to get a value because the denominator would be 0, right? So I have to manipulate a little bit more. So I noticed that I could actually divide both of those numerator terms by h. So if I divide 2xh by h, I'll get 2x. And if I divide the h squared by h, I'll be left with just the h. Okay. So if I plug in h now with 0, I will get 2x. Okay. So that was the procedural part. What the heck does this all mean? Okay. This right here is the general slope of a tangent. You guys know it's a tangent line, the slope of a tangent line, because we took the limit. Remember, the limit is what makes it instantaneous, a tangent line, okay? Now, we want to know the equation of a line specifically somewhere. At what point, right? Did they tell us what point? Right here. They tell us at 1, 1, right? So here's what you guys do. We're going to evaluate this at 1, 1. And the notation here is you draw a vertical bar. That just means evaluated at. Okay? So I'm going to write 1, 1 down below here. Now, since 2x only has the variable x, obviously we're not going to plug in the y coordinate because there is no y coordinate here, okay? So this is just going to be 2 times 1, which is 2. This right here is your specific slope. Okay? This is your slope exactly at a particular point. So going back to the very beginning, my slope is 2 whenever the point is at 1, 1. All right? I'm running out of space here. So the last thing you need to do, way back in Algebra 1 or maybe even middle school, okay? There's something called a point slope form, okay? Most of you are used to y equals mx plus b, but this form is a lot easier. I want you guys to use this here, okay? Y minus y1 equals m times x minus x sub 1. X sub 1 and y sub 1 is your point, you guys. Okay, m is your slope. So you're just plugging in what you know. So it's going to be y minus 1 equals 2 times x minus 1. And you leave it there. No need to put it into slope-intercept form. All right. So a few things to reiterate. Equation of a tangent line, we always need two things, a slope and a point. Okay? To find the slope, we need to use the derivative. You go through all your math here, you get your general slope, and then you plug in the point to get your specific slope, which is what you need. All right? So we found the equation of that tangent line. Now, why is that so important? We'll talk about that later on, okay? But at least you guys have a visual now, all right? Here's the next one. We can call this example 2, all right? Pause there while you write it down, and then press play whenever you're ready. Okay, so same idea. You have this function. It happens to be a parabola. I don't know exactly where it is. Let's see. X minus 9. So this is definitely not to scale. I could definitely use my graphing calculator or decimals just to get a picture. But this is just to get you guys to visualize it. You have some type of parabola. So in that case, let me get rid of the axes, okay? You have a parabola, and at some particular point, they want you to find the slope of that tangent line, specifically at 3, -6. That's really what you're doing here, okay? So let's do this. Here we go. Equation of a tangent line. So what do we need? Pause and play when you're ready. We need a slope, and we need a point. Okay? So we already know the point, so we're halfway done. As soon as I find out what the slope is, I can find my equation of a tangent line, okay? So how do I find the slope of a tangent line? I need to use the derivative, right? So again, I'll write it out. And again, the more you write it out, the easier it is to stick. You won't be provided this limit definition, okay? So it's the limit of f of x plus h minus f of x all over h as h approaches 0. All right? So to make things easier, we'll call this function f of x. All right? So we'll take care of the easy parts first. So I could just bring down this limit as h approaches 0. I know the denominator is just h. And then I have this f of x here. So I'm just going to go ahead and bring that down. F of x, I know, is just the function x squared minus 8x plus 9. Keep in mind that I used parentheses here. Make sure you guys always do. Now, if f of x is x squared minus 8x plus 9, how do we find out what f of x plus h is? What do you guys think we do here? Play when you're ready, okay? You're replacing every x with an x plus h. So we're going to have an x plus h squared minus 8 times x plus h plus the 9. Here, there are 2 occasions where you had an x, okay? So you want to replace it as many times as it's presented. So here we go. This right here is x plus h quantity squared minus 8 times quantity x plus h plus the 9. And if you want to color coordinate, if that's helpful, please do it. I certainly find it helpful, okay? All right, here we go. The limit as h approaches 0. So again, you guys, I believe, have a strong understanding of the concept. You know what you're trying to find. You're trying to find a tangent line specifically at a point on this parabola, okay? Now, this is where you practice your analytical skills, just knowing how to evaluate, okay? All right, here we go. So first up, x plus h quantity squared is just x squared plus 2xh plus h squared. Next up, negative 8 times x plus h. If I distribute that negative 8, I will get negative 8x minus 8h. I have that plus 9, so I'll just bring that down. Notice how I'm covering everything here, okay? Now at the end here, notice how there's a minus sign, so I actually have to distribute that negative into all 3 terms in this case. So here I have minus x squared plus 8x minus the 9. It is lengthy, but just be patient with it, okay? A lot of things go away. So I notice that x squared minus x squared will go away. I have a negative 8x plus 8x. I have a positive 9 and minus 9. Okay? So here's what I'm left with. I have the limit. Notice how I keep bringing down the limit because I haven't evaluated yet. I have 2xh plus h squared minus 8h all over h. I can't plug and chug yet because I won't get a value because of the denominator here. So I'm going to go ahead and divide every term by h. So I should get the limit as h approaches 0 for 2x plus h minus the 8. Make sure you understood what just happened there. I divided every term by h, and that's what's left, okay? Now, if h goes to 0, you're just going to be left with 2x minus 8. Think about what this means here. Pause and play when you're ready. 2x minus 8 represents the general slope of the tangent line. That's just the slope, okay? Now, I want a specific slope. So how do I do that, you guys? Exactly where do I want my slope? Specifically where? At 3 comma negative 6. So I want to evaluate. So I'll draw the evaluate bar at 3 comma negative 6. I'm running out of space here. So if you plug in 3 for x, you should get 6 minus 8, which is negative 2. That right there is your specific slope, which we could then put over here at the top. Do we have everything we need? Do we have a point and a slope? We do. So I'll write it out again. And you guys write it out until you have it stuck, okay? So this is going to be y minus my y coordinate, which is negative 6, equals the slope, which is negative 2, times x minus that 3. Okay, and I mean, I could clean up these two negatives here. Y plus 6 equals negative 2x minus 3. No need to go any further. You have your equation of a tangent line. Okay, so hopefully you guys are getting the hang of it. The biggest chunk of this work is evaluating that limit. So just take your time there. But again, don't lose meaning behind what you just found. You found a tangent line on the parabola, specifically at 3 comma negative 6. Okay? Let's keep going. So, oh, here was the picture, okay? Just to kind of confirm that. You had a parabola. You found out what the slope was. Now here it says y equals negative 2x. If you clean this up, you'll notice that it comes out to y equals negative 2x, okay? So don't let that throw you off. They like to use slope-intercept form. But why do more when you don't need to, right? Okay, here's another one. Let's call this example 3. Pause and play when you're ready. So it's the same thing, except you're dealing with a different function. So we still need to find the equation of a tangent line, which then you need a slope and a point. Okay, we know the point is at 3, 1. So all we're missing is a slope. Okay, but now we're not dealing with a parabola. We're dealing with a different function, 3 over x, right? So f of x here is just 3 over x. That doesn't change anything, okay? We're still finding the equation of a tangent line. So we need a slope and a point. And how do we find slope? We use our limit definition of a derivative. The limit of f of x plus h minus f of x all over h as h approaches 0. So I'm going to move a little bit faster here, so pause and play where it's needed, okay? All right, so we have the limit as h goes to 0. H is at the bottom. F of x, I know, is 3 over x. So f of x plus h is just 3 over x plus h. Okay. So you guys have seen this problem before. What we're going to do is, in order to subtract those fractions up top, we're going to have to multiply to get common denominator. So I'm going to multiply by x here, and I'm going to multiply by x plus h over here. All right, so here we have the limit as h goes to 0. Down below we have that h. We have a common denominator of x plus h, so I'll write that out once. Okay, now up top, x times 3 is just 3x. Now here you guys have to be careful. You have to take the negative 3 and you have to distribute it to the x plus h. So once you do that, you should get negative 3x minus 3h. That's the only time it really gets tricky, okay? Let's keep going. 3x minus 3x goes away. You guys are left with negative 3h over x times x plus h divided by h. as h goes to 0. Now recall, how do we divide fractions? We multiply by the reciprocal. So I'm going to cheat a little bit here. I'm going to erase that. And I'll multiply by 1 over h, the reciprocal. Okay, I noticed that I can cross-reduce the h factor. I'm going to be left with negative 3 all over x times x plus h. I didn't take my limit yet, so I'm going to squeeze that in there. Now, when h goes to 0, I'll be left with negative 3 over x times x, which is x squared. Again, what does negative 3 over x squared represent? That is your general slope. Now, are we looking for a general slope or a specific slope? Specific. Specifically at where? Okay, we want to evaluate this at 3, 1. So if you plug that in, you're going to get negative 3 over 9, which is negative 1/3. That right there is your specific slope that you want. I'll go ahead and put it in there. Do we have everything we need? We do. So it's going to be y minus y1, which is 1, equals the slope, which is 1/3, times x minus the x coordinate, which is 3. Leave it there. No need to simplify. Okay. Here's a visual. You have this hyperbola. Okay. And specifically, you're finding the tangent line at that point. So we found this equation. Ignore this. They wrote it in standard form, but they're just trying to get fancy. Okay? That's still the same thing as what we have right here. All right? Okay. So there's this word, differentiability. This is what we're going to end with, okay? Differentiability is finding out if a function is differentiable. Not confusing at all. Let me elaborate, okay? If you're wondering if something is differentiable, you're wondering if you can take the derivative of it. Okay? So let me show you here. Let's call this example. I think we're on 4. Where is the function differentiable? So remember, this word just means where can I take the derivative? Okay, so there are 3 cases, and I'll go over the 3 cases first before I prove it to you guys, okay? So here's the thing. If I'm standing right here, can you guys find the slope? Right? Now, for the absolute value of x, that is just the y equals x line right here. So you know the slope is going to be 1 because there's a 1 in front of that x. If I stand right here, you're standing on the y equals negative x line, right? So what's the slope of that line? Well, you go down 1, you go over 1. The slope there is going to be negative 1, right? And the slope over here was going to be positive 1. So whenever it's a line, you guys don't have to do calculus to get the slope, right? You could find faster ways. But the thing is, what happens if I ask you to find the slope right here at 0, 0? Okay, so is the slope 1? Is the slope negative 1? Right? So the thing with tangent lines is tangent lines have to be unique. Okay? Just to kind of give you a visual, this isn't the most perfect way of formally explaining it, but tangent lines are supposed to be unique, meaning you can only draw one type of tangent line. Whereas here, I could draw a tangent line here, I could draw a tangent line there, I could draw a tangent line here. Notice how there's an infinite amount of ways that I can actually draw this tangent line. Whereas with a parabola, believe it or not, there's actually only one possible way. And if you were to try to turn this even slightly, it'll intersect that curve twice, becoming a secant line. So tangent lines are unique in that way. All right? So you can't differentiate at a corner. And this is the example right here. You can find the slope everywhere else. So this function is differentiable everywhere except 0 at that corner. Okay? So the first example is you want to make sure that your graph doesn't have any sharp turns. Okay? The most popular example is the absolute value, but even if you have like a cusp where it changes dramatically, okay? Where there's a sharp turn, it won't be differentiable there. It'll be differentiable everywhere else, but not at that corner or cusp, okay? So here's the second way. If you have a discontinuity, there's no way that I can find a tangent line right where it's discontinuous. For the same reason, there's no unique tangent line. There's such an infinite amount of tangent lines right there, right? So here's the third case. You have a curve, but somewhere perfectly right at the middle, okay? And you kind of have to have a very perfect graph here. There's a tangent line. Actually, let me draw this over. I'm not happy with that. You have a curve where if you draw a tangent line, or if you find a tangent line there, that tangent line is perfectly vertical. I want you guys to think about why that's not okay. All right? If I gave you a line, you guys, a vertical line, what is the slope of this vertical line? Okay? Just for value's sake, okay? What's the slope there? So I noticed that I rise 1, but I run 0. If I rise 1 and I run 0, what happens right there, you guys? So remember, you can't divide by 0, so the slope is undefined, which is the reason why you can't have a vertical tangent, because there's no value to it, okay? So those are the 3 different ways: corner, cusp, discontinuity, and a vertical tangent. Okay? Okay, so I'm going to leave you guys with this, okay? Let's say we had x minus 2 quantity squared plus 1. I'm just making something up, okay? Actually, you know what? I think I do. Mr. Lee, you're awesome. Okay, so you have this parabola, right? Let's say I were to draw a tangent line. Okay, so right at that point right there, 4, 2, there's the tangent line. Okay. So if you look, if I start to zoom in at that point, can you guys tell which one's the curve and which one's the tangent line? And your answer should be yes. You know, it's obviously by color, but you could tell one's curving and one's linear, right? Now, what about now? Right? Still, you could still see the difference between the two. But if I go far enough, besides the color, you notice that if I zoom in so close, so arbitrarily close to that point of tangency, right? You can't tell which one's which. This is called local linearity. This is the reason why things are differentiable, okay? A very similar concept is thinking about Earth, right? This is not for you flat earthers, okay? So the world is obviously round. And then someone may argue, well, the floor is flat, so why is the earth round? It's the same concept here, okay? We know our earth, the parabola, is round. Obviously, the earth is more spherical, right? But suppose that this parabola is the earth. you know, the reason why we see things as flat is because we're so zoomed in, we're so small to the point where we can't see the curvature of the Earth, which is why it looks like a tangent line, okay? This concept is called local linearity, which is what makes things differentiable, all right? To make this a little bit more useful, let's take a look at an absolute value now, right? Which is this green function here. If you notice, can you tell which one's which? Can you tell which one is the absolute value and can you tell which one's the tangent line? Obviously you can. One is like a V shape, the other one's like a horizontal line. But let's try that same concept. What if I zoom in? Can you tell which one's which now? You can. Now what if I zoom in some more? Okay, so if you notice, if I keep zooming in, I want to zoom in like crazy here. Does the line eventually blend in with the absolute value? And it doesn't, because it's not locally linear, which is the reason why you can't have a tangent line at a corner, because tangent lines are supposed to blend in with your curve if you get as arbitrarily close as possible. So that's just to kind of prove why you can't, it's kind of a loose proof on why you can't differentiate at a corner, okay? So hopefully that gives you better context. I zoomed in all the way too, which is crazy. So going back. So that's the whole concept. You keep zooming in and a curve that is differentiable should be locally linear, meaning it should look like a line, okay? But if you keep zooming in and you still see that corner, you know it's not going to be differentiable there, all right? So recap, big takeaway, know your limit definition, know how to compute, but again, don't lose the context, okay? You're finding the slope of a tangent line, specifically at a point to make an equation, all right? That's pretty much it.